The secret data that proves our reality is a shared illusion. The graph spiked at 8:46 a.m. before anyone knew what was happening. Random number generators scattered across the world, machines designed to produce pure mathematical noise, had suddenly synchronized. In that brief window, chaos looked organized. It shouldn't have felt personal, yet it did. Data shouldn't have feelings, yet the pattern appeared as if the machines somehow sensed what billions of humans were about to feel. When researchers at Princeton saw those numbers, raw, emotionless code bending as if aware, they felt what you might feel right now. A strange mix of disbelief and curiosity clawing at reason. Could emotion itself leave fingerprints in math? That question birthed one of the most controversial databases in modern history, the Global Consciousness Project, and its mission to measure whether reality itself responds when we do. In a world built on logic, what happens if numbers start feeling too? The moment the machines reacted. In the quiet of Princeton's lab, the morning began like any other. Rows of small electronic boxes known as eggs blinked steadily, each one silently flipping bits of digital information, ones and zeros, at the same rhythm they always had. Then, somewhere near mid-morning, one researcher noticed a deviation. Several of the devices, placed thousands of miles apart across the globe, were suddenly in sync, their normally random sequences drifting toward order. Minutes later, images of smoke pouring from the first tower filled television screens. No one in the lab moved for several seconds. Even before the second plane hit, the random number generators had already registered something extraordinary. Roger Nelson, the project's founder, stared at the charts in disbelief. The data didn't make sense. Each egg was built to be isolated from external interference. Shielded electronics, independent timing, no connection to anything but power and internet. Yet as the first tower fell, the network's output lines bent upward in statistical significance. To a statistician, that meant improbability. To a human watching tragedy unfold, it meant something else entirely. The team's first instinct was error checking. Maybe the network time server had drifted, or packets of data arrived out of order. One researcher re-verified every system log. Everything looked normal. The entropy sources, quantum noise diodes, were functioning. No software faults, no synchronization bugs. Still, the pattern held. For about 4 hours surrounding the attacks, the figures refused to scatter randomly. They seemed to move together, like instruments caught in a shared rhythm of dread. What unsettled everyone was how the deviation started before any news broke. Some of the eggs had begun their divergence roughly 15 minutes ahead of the first explosion in New York. Statistically, that was nearly impossible, an anomaly far exceeding background noise. Journalists would later call it a premonition spike. Scientists refused that term, but nobody could fully explain why the data lined up the way it did. Through that day, calls poured in from other labs. The devices in Germany, Japan, and South Africa all displayed similar variance curves. Each recorded independent noise streams, yet their averages were bending in harmony. Nelson wrote quickly into the project log, possible correlation with global emotional event. That note would later ignite years of debate. Inside the lab, emotion blurred with analysis. People cried in front of monitors while copying data to backup drives. Princeton students wandered by the glass walls of the experimental room, confused by the sudden commotion. Outside, sirens howled through the streets. The researchers kept the equipment running, capturing every line of code as the world collapsed on screen. By evening, Nelson convened an urgent meeting. "We're seeing structure where there shouldn't be any," he said quietly. The group discussed possible environmental interference, geomagnetic fluctuations, network latency, power instability. None fit the timing. The anomaly appeared specific to moments of human collective attention. For contextual understanding, the team compared earlier records. The death of Princess Diana, New Year's Eve 200, major global celebrations. Each event showed similar though smaller deviations. But 9/11 eclipsed them all. The statistical graphs looked like shockwaves rolling through an invisible field. The implications were enormous. If the data was real, and not a glitch in the network, it suggested that human consciousness, collectively focused, might somehow influence systems built to be free of human bias. That wouldn't just challenge psychology or statistics, it would rewrite assumptions about physics itself. Within hours, skeptics questioned everything. Edwin May, a physicist known for his strict methodology, warned that analyzing data after the event could create illusions of pattern. "You'll always find," Order if you look backward, he said. But even May admitted the coherence was remarkable in its timing. The skeptics kept searching for a natural explanation, a power surge, satellite synchronization, anything that could produce simultaneous deviation across continents. Nothing obvious emerged. Meanwhile, the Global Consciousness Project website received thousands of messages, some from researchers asking for specifics, others from spiritual communities claiming confirmation of a collective wave. Nelson tried to keep replies factual. Data showed anomalies, not proof. Yet even he felt the weight of the coincidence. Late that night, he exported the day's data into graphing software. The red line, representing cumulative deviation from chance, curved steadily upward through the morning, peaked as the South Tower fell, and plateaued by midnight. The plot looked hauntingly intentional. When compared to random simulations, the probability of such a curve occurring by accident hovered near 1 in many thousands. Not impossible, but disturbingly rare. In conversations afterward, team members confessed how difficult it was to separate scientific judgment from emotional context. They were living the same shock as the rest of the planet. One of them wrote in a personal note, later shared anonymously, "I don't know what's worse, believing that our machines reacted with us, or believing it's only coincidence while knowing how it felt." Outside peer reviewers eventually analyzed the dataset independently. Some found minor statistical artifacts, others confirmed a small but notable deviation. Everyone agreed on one thing: the network had behaved differently that day. For Nelson and his colleagues, this wasn't a discovery they could celebrate. It was unsettling proof, if one accepted it, that something collective, intangible, could register in physical hardware. Whether that something was human emotion, attention, or synchronized stress remained uncertain. But the pattern had etched itself into the GCP's history forever. As the team archived the data, they faced a deeper realization. Their instruments had become inadvertent witnesses to history, capturing not just random bits, but maybe the resonance of human experience itself. The next morning, before anyone could fully understand what had happened, Nelson wrote the line that would define the entire project. To understand this moment, we must look at how the idea of measuring mind began. And that's where our story rewinds, to a quiet basement at Princeton, decades earlier, where engineers first dared to ask whether thoughts could move machines at all. Princeton's quest to measure the mind. Decades before anyone talked about global consciousness, a handful of engineers and psychologists at Princeton University started chasing a quieter mystery. In the late 197s, the idea that thoughts could influence matter wasn't something physicists took seriously. But in a small, windowless room inside the School of Engineering, a curious collaboration began. Robert John, then dean of the school and an expert in spacecraft propulsion, had supervised experiments on plasma thrusters and rocket fuels. He was as technical as scientists came, but one student's odd question changed his direction entirely. She asked if her mind could affect the outcome of a machine. Most professors would have laughed. John didn't. Instead, he designed an experiment to test it. That impulse eventually became the Princeton Engineering Anomalies Research Laboratory, known as PAIR. His logic was straightforward. If human intention could nudge a physical system in any measurable way, it would be visible at the smallest scale, in randomness itself. So PAIR began building devices that produced random bits using quantum noise. If, through focused intention, volunteers could shift the statistical output even slightly away from 50-50 odds, it might mean consciousness had a measurable footprint. Early tests were simple. An operator would sit in front of a blinking box that emitted a rhythmic cascade of ones and zeros. Their task was to mentally push the machine toward more ones or more zeros. For hours, subjects stared, concentrated, and logged data. Then computers analyzed the results. Over thousands of sessions, small deviations appeared, tiny but consistent. The odds of pure chance producing those patterns were surprisingly low. John and his research partner Brenda Dunn called it Micropsychokinesis. Within a few years, they had billions of data bits and what looked like a statistically significant effect. The average shift was minuscule, about a 10,000th of a bit per bit recorded, but with massive sample sizes, the significance compounded. In conventional terms, that meant a correlation equivalent to 7 standard deviations beyond what random theory predicted, something that should happen only a few times in a universe's lifetime if it were purely noise. The results drew excitement and criticism in equal measure. Physicists dismissed them as artifact. Psychologists accused John of wishful statistics. yet others saw the beginnings of a new frontier. Even skeptics admitted the experiments were run with rigorous documentation, shielding, and independent verification. The question wasn't whether the numbers drifted, it was why. Inside the Pear lab, volunteers who participated weren't mystics. They were engineers, students, even janitors curious about the thought-machine link. They would relax, focus intention, sometimes meditate, sometimes joke their way through sessions. John noticed that pairs of participants who had a close bond, a couple, or two friends who genuinely liked each other, produced stronger effects than individuals. Emotional connection, it seemed, improved performance. Bonded pairs became a formal category in their datasets, hinting that relationship, not just mental effort, mattered. As the experiments continued, another oddity emerged. Distance didn't seem to weaken the results. People could influence machines even when separated by miles, as long as there was a sense of connectedness or shared purpose. Pair ran remote intention tests where participants sent mental focus to a machine located elsewhere, and the patterns still shifted slightly. They even performed retroactive experiments, where intention was applied after data had been recorded, as if mental focus could reach backward in time. The statistics once again showed small but measurable effects. Within academic walls, those ideas were radioactive. Critics pointed to the likelihood of unconscious bias or flexible data windows, choosing when an effect started and ended. Meta-analyses later suggested that experimenter expectations could subtly influence outcomes. John countered with replication. The lab repeated trials under double-blind conditions, using automated protocols that eliminated human selection entirely. The deviations, though still small, persisted. Pair's work slowly evolved from curiosity to long-term data collection. Over 12 years, they amassed billions of trials. Bayesian reanalysis showed probabilities so steep that, to believers, only mind-matter interaction could explain them. Still, the effect sizes were too tiny to change real-world physics. You couldn't turn a screw with thought, but you might tip an electron's path ever so slightly. Dunn liked to call it the whisper of consciousness at the edge of chaos. Behind the numbers lay a philosophical question. If the observer could subtly shape outcomes, where did observation end and influence begin? Quantum physicists discussed the observer effect in theory, but Pair was attempting to catch it in hardware. Their random number generators worked through electronic noise, unpredictable even under perfect isolation. In theory, nothing physical inside should respond to a person sitting across the room. Yet over and over, the aggregate data leaned just enough to tease possibility. Not everyone outside Princeton dismissed them. The lab attracted collaborations from visionary thinkers and parapsychologists worldwide. Conventions buzzed with the implications for human potential. If consciousness could interact with randomness, it might underpin phenomena like synchronicity, coincidence, even ESP. But mainstream science wanted mechanisms, not metaphors. The hypothesis lacked any mathematical model tying mental intention to electron behavior. John admitted as much. We can measure what happens, but not explain how it happens. By the early 199s, funding grew tight and skepticism louder. Academic journals rarely touched the subject. Reviewers demanded replicable physics. Still, the lab endured, sustained by private donors intrigued by its audacity. Roger Nelson, a psychologist with a background in experimental design, joined during these years. His fascination wasn't in laboratory psychokinesis, it was in collective experiences. If individuals could produce microscopic effects, what happened when millions focused attention on a single event? A meditation, a disaster, worldwide joy. Could emotional resonance itself leave a statistical fingerprint? Nelson began archiving Pair's databases, noticing that intention seemed to interact most strongly when meaning was high: birthdays, ceremonies, anything with deep emotional charge. He started imagining a network of machines scattered around the world, continuously logging randomness, to see whether global emotional moments could synchronize them. The concept sounded science fictional, a world detector for consciousness. That idea gestated quietly, while Pair continued publishing mixed results. A parallel wave of studies elsewhere attempted to replicate them using new quantum random sources or internet-connected devices. Some succeeded modestly, others found nothing. A 2018 large-scale meta-study, using ultra-precise quantum hardware, concluded there was no measurable influence of intention on randomness. It favored the null hypothesis, arguing earlier deviations likely stemmed from statistical quirks or publication bias. But even those critiques acknowledged pairs' unusual consistency. They had produced something that refused simple dismissal. Within the community, debates raged between those who saw evidence of a subtle link and those who saw noise elevated to myth. John's final published statement before retiring captured the divide. Our findings challenge material assumptions, but data itself has no prejudice. Interpretation is our burden. When the university eventually closed the pair lab in 2007, boxes of equipment and mile-long tapes of numbers were archived. To most, it looked like the end of an eccentric project. But for Nelson, it was only a starting point. He saw in that enormous dataset the seed of a larger vision, one that would extend beyond individuals and small labs to the entire planet as an instrument. While others dismantled equipment, Nelson was sketching network maps. Each node would be a random number generator linked through the internet, sending continuous data to Princeton. If something global stirred human hearts, terror, grief, unity, he would check whether the world's noise lost its randomness. It would be the largest mind-matter experiment in history. And so, out of a question once asked by a curious student, "Can thought move a machine?" grew a blueprint for asking something much larger. Can millions of thoughts, felt together, move reality itself? That blueprint would soon become a functioning network known as the Global Consciousness Project. And before long, it would produce data no one could easily ignore. Birth of the Global Consciousness Project. Roger Nelson's idea took shape quietly in the late 199s, inside a modest office stacked with servers and circuit boards. He'd spent years watching single random number generators react to human attention in the pair lab. But the pattern that fascinated him most wasn't individual, it was collective. Every time something stirred global emotion, from Princess Diana's funeral to New Year's fireworks, pairs' archive devices showed faint but synchronized deviations. Nelson wanted to know whether the entire planet, through shared consciousness, could register in machines designed to feel nothing. That question became his new obsession. He called it the Global Consciousness Project, or simply GCP. It started as a network of just a few hardware-based random number generators, each nicknamed an egg. The devices weren't mystical. They were electronic boxes that produced streams of random bits using quantum noise sources. Each unit sat connected to a local computer that time-stamped its data and sent it via the internet to a central server at Princeton. There, Nelson's software monitored the constant pulse of zeros and ones, looking for statistical order where there should be none. At first, the project was almost experimental theater, a handful of scientists and technicians scattered across continents agreeing to plug in devices that did nothing but hum randomness. The data trickled in, thousands of bits per second per node, from cities like Delhi, Paris, Buenos Aires, and Tokyo. Each egg was independent, but together they formed a global grid that never slept. Nelson's team checked time synchronization, calibrated entropy sources, eliminated network biases. When the numbers flowed smoothly, he smiled, not because they proved anything yet, but because humanity had built a nervous system for its own emotion. The initial months were uneventful. Statistical graphs wobbled as expected, pure stochastic noise. Then came the death of Princess Diana in 1997. Around that global moment of shock and mourning, Nelson noticed small but measurable deviations. It wasn't dramatic, but clearly distinct from baseline. He logged it meticulously, notable variance from chance during high-impact emotional event. It might have been coincidence, but it fit the pattern hinted at in pairs' archives. Something collective might be rippling through the data. He decided to formalize the operation. By 1998, GCP established a consistent network architecture with continuous bit generation, local redundancy, and automatic transmission to a secure database. Volunteers and collaborating researchers around the world hosted eggs in homes, observatories, universities, and private labs. At its peak, there were more than 60 active devices across multiple continents, tiny, quiet witnesses to human events. Each egg produced 200 random bits every second. These bits were aggregated into minute, hourly, and daily datasets. On normal days, output plotted near perfect randomness. But when something stirred global attention, terror attacks, mass protests, royal weddings, or large-scale meditations, slight departures emerged. Individually, those deviations meant nothing. Collectively, over hundreds of millions of data points, they began forming a peculiar fingerprint. Researchers debated how to define an event. Nelson created a registry of pre-announced periods linked to major global news or cultural happenings. After each one, the data was analyzed statistically to see if variance exceeded expected randomness. Over time, a pattern built up. When human emotions synchronized worldwide, the network's randomness sometimes wavered toward order, as if empathy itself left a trace. Lab culture around GCP was unusually open. Nelson posted the entire dataset online, inviting anyone, supporters or critics, to verify findings. This transparency drew both admiration and attack. Skeptics pored over the numbers looking for flaws, while parapsychologists hailed it as revolutionary evidence for a global mind. Nelson ignored labels and kept plotting graphs. In one document, he described how the network reminded him of a seismograph measuring not Earth tremors, but psychosocial quakes. Just as the Earth's crust responded to tectonic tension, perhaps the fabric of information itself responded to human attention. It wasn't a theory most physicists would endorse, but it captured the spirit of the work. Within a couple of years, GCP started correlating its anomalies with emotionally charged moments. The Kosovo conflict, large global meditations for peace, New Year's Eve transitions, even the remarkable global mourning after Mother Teresa's death. In each case, Nelson and collaborators found small but consistent statistical departures clustering near the times of maximum collective focus. The effect sizes were tiny, barely fractions of a percent, but intriguing enough to demand further study. Every time the graphs bent slightly, the interpretive battle reignited. Bayesian analysts argued that given enough events, some variance would appear significant by pure coincidence. Nelson's team countered with cumulative analysis that showed a gradual build-up over years exceeding chance expectation. They calculated a global figure averaging out to odds of less than 1 in 100,000 that the deviations were entirely random. Supporters saw a signal emerging from noise. Critics saw noise searching desperately for meaning. Despite debates, the project gained cultural traction. Documentaries and books started referencing the quantum consciousness network. Popular media, hungry for mystery, called it the world's emotion detector. Spiritual communities adopted GCP plots as proof of mass meditation effects. Nelson always tried to correct misconceptions. We're observing correlation, not causation. Yet deep down, he admitted fascination bordering on belief, that maybe consciousness did ripple through physical systems in ways science hadn't mapped yet. In the late 199s, funding came from small grants and individual donors rather than institutions. Mainstream science remained cautious. The idea of measuring global emotion with electronics still verged on parapsychology. But Nelson's credentials and the project's rigorous data handling lent unusual credibility. The intentional neutrality, no metaphysical claims, just data and probabilities, kept skeptics engaged. By 200, GCP expanded its reach further. Nodes were placed in remote areas to check whether anomalies were spatially correlated or truly global. They weren't local disturbances. The variance appeared simultaneously across different regions, reinforcing the impression of an overarching influence. Nelson began speaking at conferences about coherent patterns of deviation under conditions of shared attention. The phrasing was careful, not proof of telepathy, but an empirical observation that defied easy explanation. He recalled one particularly moving instance, the global celebrations welcoming the new millennium. As the clock struck midnight in each time zone, the network displayed synchronous fluctuations that traveled like a wave following human joy around the planet. It wasn't large enough to declare discovery, but enough to electrify supporters. For a few hours, Nelson wrote, the world's noise became slightly more orderly, as though collective excitement brushed the circuits with meaning. Still, belief wasn't proof. Statisticians warned that without predictive models, clear hypotheses registered before events, the correlations risked being identified after the fact. Nelson accepted that criticism, implementing predefined event protocols to reduce bias. But he knew that sooner or later, a massive, undeniable world event would test the system beyond dispute. Something emotional enough to engage nearly every mind on Earth. He didn't know when it would happen, but he suspected that when it did, the network of glowing eggs would show whether global consciousness was more than metaphor. In the calm before that test, the data hummed continually day and night. Graphs updated every minute, accumulating thousands of lines that looked like meaningless static, until they didn't. Nelson often walked through the Princeton lab late at night, rows of LEDs blinking like small digital heartbeats. To him, Each represented a fragment of humanity's shared awareness, a pulse not of circuits, but of attention itself. When asked if he truly believed machines could sense emotion, he paused. "Maybe it's not the machines sensing us," he said softly. "Maybe they're just mirrors, showing us how connected we already are." That line wrapped around you like a quiet dare. What if that mirror really is reflecting us, all of us, blinking silently in sync whenever the world holds its breath? Those words would become prophetic, because within a year, the world would face a tragedy that united billions in shock and grief, and the Global Consciousness Project's instruments would record their most dramatic signal yet. For Nelson, it would mark the moment his quiet experiment stepped out of anonymity and into history, the moment when numbers and emotion collided on a scale no one could ignore. Everything that followed would turn this modest network of random noise into one of the most debated studies in modern science, and for many, the first real evidence that maybe, just maybe, our reality moves when we do. The 9/11 spike, coincidence or connection? On the morning of September 11th, 2001, the Global Consciousness Project's network of eggs was already awake, quietly churning bits into its servers at Princeton. At 8:46 a.m., when Flight 11 hit the North Tower, several of the devices began showing the same slow drift toward order they had displayed during earlier world events. But this time, the amplitude exceeded anything in the database. The network that normally looked like static started forming a smooth curve. Nelson and the analysts who happened to be on campus saw the curve before anyone turned on the news. They were watching probability itself bend while the world still thought it was another clear Tuesday. When reports of a plane crash arrived through the lab's radio, the team froze. No one connected the dots yet, but as television images filled the office, the lines on their monitors rose higher. At 9:03 a.m., as the South Tower was struck, every active egg on 3 continents showed correlated deviation. To statisticians, it meant variance clustering far from where chance said it should sit. To the humans watching live tragedy, it felt like the instruments were grieving too. The hours between the first impact and the tower's collapse passed in silence, punctuated by printer noise and quiet sobs. Analysts checked power feeds, local clocks, and network latency. They expected an error cascade somewhere, perhaps interference from overloaded routers or an electromagnetic burst from broadcast towers. Everything checked out. The physical environment was stable, yet the lines kept curving upward, the unmistakable mathematical signature of reduced randomness. What struck Nelson later was that the deviation seemed to begin before the attacks, around 8:30 a.m., 15 minutes ahead of the first collision. No world event had been declared. The world's focus hadn't shifted yet. Still, the random streams had started drifting toward coherence. He wrote a short field note, "Unexplained pre-event structural anomaly." It would become one of the most scrutinized phrases in GCP history. By early afternoon, he reached out to collaborators in Europe and Asia. Their local data mirrored Princeton's. Machines in Switzerland, India, and Australia, all thousands of miles apart, had produced nearly identical variance patterns. Timestamps aligned within seconds, defying the expectation that noise in different hemispheres should remain uncorrelated. For Nelson, this synchronization hinted at something global, unseen, yet measurable. The emotional atmosphere inside the lab mirrored the rest of the planet. Researchers alternated between disbelief and a grim determination to keep recording. Some gathered around a small television, others around data plots. No one claimed discovery. They simply didn't understand how blind electronics could react in step with human shock. "Keep the system running," Nelson instructed. "History is happening, and the numbers will tell their version." As midnight approached, cumulative deviation exceeded thresholds the team had set for statistical significance. The detailed graph showed a climb beginning just before the first plane, peaking at the tower's fall, gradually returning to baseline as the day closed. When averaged across all nodes, the odds of such a pattern appearing randomly were roughly 1 in several 100,000. In scientific terms, it was suggestive, not proof, but undeniably odd. Within 24 hours, the data began circulating online. The GCP's website posted an annotated graph titled Cumulative Deviation on September 11th. Visitors flooded the servers, crashing pages. Some saw it as evidence of a planetary consciousness shockwave. Others accused the project of exploiting tragedy. Nelson avoided interviews, releasing only a brief statement. "Our results show a modest statistical departure during the events of September 11th, consistent with our past findings, though not conclusive of any causal mechanism." Behind that cautious language was turmoil. Colleagues from PAIR, including Brenda Dunn and Robert John, reviewed the datasets. They confirmed that the anomaly could not be traced to hardware malfunction. But skeptics quickly entered the conversation. Edwin May and other independent analysts argued that selecting analysis windows after the event could create false positives. They performed alternative tests using fixed time sequences, which reduced significance to marginal levels. To them, it was coincidence painted with meaning. Still, even those critiques conceded that September 11th's magnitude made it a perfect stress test. If the hypothesis was that collective emotion might influence randomness, never before had global attention been so unified, so charged with collective sorrow. Whether correlation implied connection remained the open wound. Mainstream statisticians tried replication using alternative models. Some found the deviation shrank when corrected for multiple comparisons. Others observed that the effect, though smaller, persisted across data subsets. For Nelson's camp, the persistence mattered more than the size. If consciousness could influence matter at all, even infinitesimally, the philosophical implications dwarfed the p-values. Around campus, whispers spread that Princeton was hosting a real-life experiment in psychic physics. The university's press office downplayed the rumors. Inside the GCP offices, staff processed terabytes of numeric logs searching for mundane causes: electrical surges, cosmic rays, temperature drift. None matched the synchronized global phase shifts. The anomaly was either an extraordinary statistical fluke or something that pointed beyond familiar physics. In the months that followed, the debate crystallized. Peer reviewers who leaned skeptical published reanalyses claiming that when data windows were pre-registered, the anomaly lost significance. Parapsychology journals countered with meta-studies showing that the cumulative GCP database, over 250 events recorded, now exhibited a slow but steady accumulation of deviations larger than chance prediction. The argument became philosophical. Is probability itself stable, or does human meaning distort it under emotional mass? Nelson collected responses, sometimes defensive, sometimes weary. In correspondence he wrote, "We never expected belief. We expected curiosity." He understood the fragility of evidence when emotion runs high. Yet privately he admitted that watching the data peak exactly during the collapse felt eerie, almost sacred. "If coincidence, it is the strangest one I have ever seen," he told a colleague. For many outside observers, the timing alone was enough to spark fascination. Documentaries picked up the story, framing the GCP as the world's first sensor of the human soul. Others labeled it modern superstition dressed as science. Ironically, both camps kept visiting the openly published data. Transparency became the project's defense. Anyone could download, analyze, and decide. One independent physicist attempted to model potential physical mechanisms. He suggested that simultaneous emotional arousal worldwide could subtly alter electromagnetic noise in communication networks, thereby influencing electronic random sources indirectly. It was an interesting but unproven idea. Measurements of global magnetic fields during 9/11 showed no corresponding disturbance. Still, it kept dialogue alive between hard physics and speculative consciousness studies. The emotional gravity of the event blurred lines between objective measurement and human experience. In one internal memo, a staff member wrote, "Maybe we're not measuring consciousness changing the machines. Maybe we're recording how meaning reorganizes perception itself." To some, that statement encapsulated the entire struggle, whether the GCP data reflected genuine physical influence or the human compulsion to see order in chaos. Over time, Nelson began to view 9/11 less as confirmation and more as a mirror. The project had exposed how data can become an emotional symbol. Every spike, every downward drift, carried a narrative, and humans are wired to chase narrative. Yet, the numbers remained. The curve on that chart refused to vanish under scrutiny. Even when recalculated with conservative parameters, slight coherence persisted. A 2002 joint paper summarized the paradox neatly. The observed deviations are small and ambiguous, but collectively improbable. They may represent either the psychology of interpretation or an as-yet undefined coupling between consciousness and random processes. It was a statement of balanced uncertainty and a challenge to both believers and skeptics. Looking back, the 9/11 spike became the defining test case for the Global Consciousness Project. Every later argument, for or against, circled around that day. To proponents, It marked the first time human emotion visibly synchronized machines worldwide. To critics, it was evidence of how tragedy amplifies bias and how randomness invites projection. Nelson himself leaned neither direction publicly. In lectures years later, he displayed the same 9/11 graph and simply said, "This is what we recorded. Interpret it as you will." Students often asked whether he personally believed consciousness caused the shift. He'd smile and reply, "I believe the data are real. The rest is the question." Behind that restraint was quiet conviction that even if the machines weren't responding to minds, they at least captured the rhythm of meaning spreading through them. For a scientist trained in controlled systems, that realization was almost mystical, that measurement itself might participate in what it observes. As analyses faded into academic archives, one truth persisted. On that September morning, when the world's attention merged into a single heartbeat of fear and grief, hundreds of random number generators scattered across the globe veered from chaos into mild coherence. Whether coincidence or connection, the pattern remains in the database, frozen in bits, evidence of a day when emotion and mathematics briefly spoke the same language. Breaking down the data. For all the speculation, mystery, and emotion swirling around September 11th's strange data curve, one thing remained essential. Numbers, not feelings, would decide whether the Global Consciousness Project's claim held weight. The moment the initial shock wore off, Nelson and his colleagues knew that sentiment wouldn't convince anyone. The only hope for credibility was in the mathematics underpinning every recorded anomaly. So they turned back to the raw data itself, the second-by-second streams of zeros, and ones that represented the heartbeat of their project. Each random number generator, or egg, spit out a continuous sequence of bits, 200 per second. Under normal circumstances, half of them should be ones, half zeros, fluctuating randomly within predictable statistical bounds. Over a full day, each device produced around 17 million bits. Aggregated across 60 nodes worldwide, that meant billions of data points. The analysis required wasn't guesswork, but precise statistical scrutiny. Research assistants at Princeton wrote scripts to compute variance from expectation, essentially quantifying how far the real output drifted from true randomness. If a curve consistently leaned even fractionally off the baseline, there could be reason to suspect influence, either environmental or something more elusive. To visualize this, Nelson used a tool called a cumulative deviation graph. Imagine flipping a coin thousands of times. You'd expect roughly half heads, half tails. If you plotted your running total difference from expectation, the line would meander but stay near zero. Yet if, at some point, forces shifted the odds even slightly, the line would drift steadily upward or downward. That was the GCP's key metric, the slope of improbability. On ordinary days, the graph jittered like static. During major world events, those jitters sometimes coalesced into long, smooth arcs, signals rising out of noise. But patterns can mislead. The human brain seeks meaning in chaos, and statistics is full of traps that turn randomness into apparent order. To counter accusations of cherry-picking, the GCP developed strict analytical rules. Each formal event had to be defined before examining data. Teams worldwide maintained an event registry describing start and end times for significant global happenings: natural disasters, deaths of public figures, holidays, political crises. Only after these parameters were fixed did analysis proceed. The intent was to guard against the temptation of drawing boxes around interesting spikes after seeing the graphs, what statisticians call post hoc analysis. Critics, however, argued that subjectivity still lingered in event selection. What exactly qualifies as a global emotional event? Who decides its timing? A disaster in one region might dominate headlines there, but barely register elsewhere. Any ambiguity in selection could amplify false positives, a phenomenon known as selection bias. Even Nelson admitted that defining the world's attention was an art more than a science. Still, successive reviews by outside analysts confirmed that, regardless of how events were chosen, the probability distribution of deviations across the entire 20-year dataset leans subtly away from total randomness. Statistically, the global effect size across hundreds of registered events hovered around 0.3% deviation, minuscule yet persistent. In standard deviation terms, this equated to roughly 3 sigma over cumulative analysis, translating to odds against chance of about 1 in 1,000. Impressive enough for curiosity, not strong enough for scientific proof. Yet consistency mattered more than magnitude. Whenever humanity collectively focused, be it war, celebration, tragedy, or triumph, the lines bent just slightly. The question was why. Data specialists from outside fields offered competing interpretations. Some proposed the anomalies came from shared environmental factors. Global power grid oscillations, solar storms, or network latency during high traffic could impose correlated noise across electronic systems. The GCP team tested these. They monitored geomagnetic indices, solar flux, and even internet backbone statistics during recorded anomalies. None tracked neatly with the deviations. Power supplies remained stable, solar indices flat. If correlation existed, it wasn't through conventional electromagnetic channels. Statistical purists examined methodology instead. They accused GCP of non-independence, treating each event as separate when, in reality, overlapping time windows could inflate apparent probability. Nelson's group responded by running permutation tests, scrambling event orders, reconstructing datasets as if world history had unfolded in random sequence. Even then, authentic chronology produced slightly greater deviation than simulated versions. The difference persisted stubbornly, like an itch that refused mathematical scratching. Another issue was multiple comparisons, running so many tests that occasional big results appear by luck. With hundreds of global events logged, critics argued that at least a few would show spurious significance. Nelson embraced transparency, publishing every analysis online, including null results. When the total database was treated as one giant meta-experiment, the global cumulative z-score remained just above accepted thresholds for significance. Not decisive, he wrote, but improbable enough to keep asking questions. In 2017, physicist Peter Bansal, once an enthusiastic collaborator, published the most comprehensive review to date. His conclusion was blunt. The data failed to support the core global consciousness hypothesis. According to Bansal's Bayesian modeling, observed correlations were better explained by methodological artifacts and goal-oriented data handling. He proposed that experimenters, consciously or not, introduce structure through their decisions about event periods. In his words, the effect follows the intention of analysis rather than the underlying physics. For the parapsychology community, this stung deeply, yet even Bansal acknowledged an undeniable statistical oddity. Small, persistent correlations existed, just not in ways that confirmed any particular theory. Nelson responded calmly, saying the findings didn't negate the broader question. Absence of proof isn't proof of absence, he wrote on the project's website. He agreed that data interpretation shapes outcomes, but so does skepticism. To him, the database was less about detecting psychic influence and more about revealing unexpected structure in complex global systems, including human analysis itself. That framing turned the GCP from experiment into mirror, showing how interpretation creates reality as much as observation does. Meanwhile, independent statisticians ran new checks using blind computational audits. They fed GCP's decade-long bit streams into algorithms designed to detect non-random periodicities. Beyond the registered emotional events, patterns still surfaced, a faint diurnal rhythm linked to synchronized network behavior around human activity cycles. Even when controlling for such effects, residual anomalies persisted during moments of intense media coverage. Perhaps those spikes weren't proof of consciousness, but signatures of a hyper-connected world reacting in unison through technology itself. Still, not all anomalies fit convenient sociological explanations. During mass meditations, events drawing no technological surge, the same patterns occasionally appeared. The probabilities shrank again to mere fragments beyond chance, yet their stubborn repetition echoed pairs' earlier micropsychokinesis data. Each dataset whispered the same question in numerical form. Why does meaning seem to coincide with measurable order? Philosophers of science noticed another layer. Observer bias, not just in analysis, but in belief itself. Supporters expected coherence, skeptics expected noise. Quantum mechanics already taught that observation couldn't be entirely detached from outcome. Was the GCP inadvertently testing not human consciousness versus machines, but human expectation versus meaning? Nelson loved that paradox. Perhaps, he mused in a talk, the effect we measure is the struggle between belief and disbelief itself, a collective cognitive interference pattern. Outside academia, popular writers simplified it differently. The world's emotional field makes random systems resonate. But inside the data rooms at Princeton, equations told a murkier story. an accumulation of extremely small improbabilities hinting at order and chaos. Each new dataset added another thread to that tapestry, simultaneously credible and incredible. In the end, after hundreds of analyzed events spanning more than 2 decades, the consensus among independent statisticians leaned toward conventional skepticism. The GCP's deviations, though statistically interesting, fell below rigorous thresholds required to overthrow known physics. Yet even skeptics admitted respect for its transparency and sheer database magnitude. Unlike many fringe projects, GCP invited challenge openly. "If there's a mistake," Nelson often said, "let the data show it." What the data ultimately showed depended on the eyes interpreting it. To a mathematician, it was a beautifully stubborn anomaly, stuck between ordinary noise and extraordinary implication. To believers, it was evidence that human minds participate in reality's hidden order. To critics, it was a lesson in how easily data bends under the weight of expectation. By the late 200s, GCP's once thrilling graphs had become a canvas for philosophy. They captured the tension between faith in numbers and faith in meaning, between the demand for proof and the allure of mystery. Whether the deviations pointed to collective consciousness or statistical happenstance, they accomplished something undeniable. They made humanity look closely at its own reflection in data. As one researcher summarized after years of examining endless spreadsheets, "Maybe the anomaly isn't in the machines. Maybe it's in us, in how we track our feelings through numbers and expect the universe to care." Even as equations reduced mystery to marginal significance, people kept returning to those curves, the tiny waves of improbability that seemed to breathe when the world held its breath. The math might have crumbled under scrutiny, but the fascination refused to die. Because somewhere between error bars and empathy, the question still glimmered. If randomness itself wavers when billions feel the same thing, can we still call it random at all? The other labs that tried to prove it, while the Global Consciousness Project became the most visible attempt to measure a worldwide mind, it wasn't the only one chasing the same ghost. Across a loose constellation of independent research centers, other scientists and visionaries were building parallel experiments to test whether thought could nudge matter, or at least leave a detectable fingerprint inside physical systems. Some adopted hard lab procedures, others leaned toward spirituality cloaked in data analysis. Each claimed to edge slightly closer to proving that consciousness interacts with the material world. Together, they formed what some insiders jokingly called the Quiet Network, groups convinced that if the GCP hinted at a signal, the world needed more antennas listening. The first branch was the old pair lineage, continuing under private funding even after Princeton officially closed its doors in 2007. Former collaborators, now unaffiliated academics, kept running micropsychokinesis experiments with updated hardware. Their premise stayed simple. If focused intention could bias random events, repetition over years should clarify whether the deviations were real or statistical fantasy. They built new quantum random number generators using photon polarization instead of diode noise, hoping to eliminate any deterministic artifacts. Some results echoed the original pair statistics, tiny drifts borderline significant, but the leaps of faith remained large. To the skeptics, this was déjà vu. To believers, a quiet persistence of the same small miracle repeating itself. Then came a different kind of institution, the Institute of Noetic Sciences, or IONS, founded by Apollo 14 astronaut Edgar Mitchell. Mitchell's epiphany during his return from the moon, an overwhelming sense of unity with all existence, pushed him to create a research facility dedicated to exploring consciousness beyond the brain. Decades later, IONS researchers were running studies paralleling GCP's approach, yet interpreted through a cosmic lens. Instead of viewing randomness as mechanical noise, they saw it as a doorway between mind and matter. Their laboratories tested whether human intention, meditation, or even remote emotional connection could measurably alter physical or informational systems. By the 201s, IONS scientists were hosting mass participation experiments online. Volunteers worldwide would synchronize through timed meditations, while quantum random number generators streamed data in real time. The hypothesis, collective coherence, aligned emotional states, might subtly organize randomness the way flocks of birds self-align. Some sessions yielded the faint deviations familiar from pair and GCP, others produced flat lines of pure noise. Statistically, results hovered near neutrality. What mattered wasn't proof but participation. Tens of thousands joined global intention days, turning science into a kind of secular ritual. Those moments hinted at a psychological truth even skeptics accepted. When people act as if they're connected, their physiology synchronizes, heart rates, breathing, neural patterns align in measurable ways. Whether that synchrony extended into the electronics was still unknown. The HeartMath Institute, meanwhile, took the idea of coherence literally into biology. Founded in California in the early 199s, HeartMath began as a study of how emotional states affect heart rhythms. Its researchers discovered that when people felt gratitude or compassion, their heart rate variability, a subtle rhythm in heartbeat timing, became harmonious, a condition they called coherence. Over the years, the Institute proposed a larger possibility. Coherent hearts might communicate electromagnetically, synchronizing groups through fields measurable outside the body. When enough individuals worldwide generated positive emotions simultaneously, perhaps the Earth's magnetic environment itself could respond. This concept matured into the Global Coherence Initiative (GCI), HeartMath's answer to GCP. Instead of random number generators, GCI used magnetometers buried around the world, tracking fluctuations in the planet's magnetic field. Data streamed into servers 24 hours a day. Researchers correlated spikes and dips with major world events, eclipses, mass meditations, even global tragedies. In several instances, magnetometer readings apparently shifted in tandem with heightened collective emotion. Critics saw ordinary geomagnetic variation. Supporters saw a planetary heartbeat reacting to human feeling. HeartMath's public outreach amplified the idea into something more participatory than GCP's passive sensors. They taught biofeedback techniques enabling individuals to increase personal coherence and invited everyone to contribute to global heart synchrony events. From a scientific viewpoint, the evidence for field interaction remains circumstantial. Yet their physiological research, showing real, measurable links between emotional regulation and brain function, gave them more mainstream credibility than most consciousness groups. Even so, the leap from heart rhythms to shifting Earth's magnetism was immense. Inside the scientific community, most admitted admiration for HeartMath's data collection, while withholding endorsement of its most sweeping claims. Back at IONS, new projects targeted the threshold between psychology and physics. Researchers launched double-blind experiments to test whether intention could alter the entanglement state of photons in quantum apparatuses. They reported small effects that, like GCP's data, barely peaked above statistical noise, yet repeated often enough to tease curiosity. Peer-reviewed journals debated methodology. Meta-analyses alternated between mild support and dismissal. The strongest consensus emerging from decades of worldwide trials was paradoxical. If mind-matter interactions exist, they're extraordinarily subtle, so subtle that proof itself becomes a matter of interpretation. Despite limited acceptance, these laboratories influenced culture far beyond academia. Documentaries framed their combined work as evidence of a dawning age where consciousness shapes reality. Meditation apps referenced HeartMath's coherence graphs. Online communities tracked GCP and GCI data alongside moon phases and stock markets. Each spike or dip became a Rorschach test for believers seeking cosmic pattern. For the researchers keeping the equipment calibrated, enthusiasm was both blessing and curse. Funding surged, credibility lagged. Among them persisted a quiet realism. "We might never reveal a mechanism," said Roland McCready, HeartMath's research director. "But if the data inspires people to act with greater care, maybe that's the real coherence we're detecting." That sentiment echoed within IONS halls, where scientists blended laboratory rigor with meditative practice. They often described their work as bridging external measurement and inner experience. To them, verifying influence was secondary to demonstrating interconnectedness as a lived phenomenon. Critics in mainstream physics used harsher language. They accused noetic and coherence studies of blurring scientific boundaries, dressing spiritual intuition in statistical costume. Papers pointing to minuscule effect sizes were dismissed as classic examples of p-hacking, where large datasets are mined until chance appears meaningful. Yet the openness of both IONS and HeartMath frustrated detractors. Their databases, like GCP's, were fully public, allowing anyone to test claims. Transparency kept the conversation alive, even among skeptics who privately admitted fascination with the persistence of those small, stubborn anomalies. Together, these groups formed a mosaic of modern parapsychology's evolution, From Pair's hardware tests to GCP's global network, from IONS mind experiments to HeartMath's physiological coherence sensors. The narrative thread connecting them was simple. Wherever human hearts and minds moved in sync, physical systems sometimes wobbled in ways statistics struggled to classify. None of it amounted to confirmation, yet none of it fully disappeared under scrutiny either. By the 202s, cross-communication between projects intensified. HeartMath's magnetometer data occasionally overlapped with GCP's random output spikes. When global attention focused on major events, both systems sometimes responded, though correlation lines remained thin and debated. Collaborative papers cautiously suggested that environmental and consciousness variables might intermix, that geomagnetic fluctuations could act as intermediary carriers for psychological collective states. To outside observers, such speculation bordered on metaphysics. To participants, it hinted at a unifying field connecting biology, technology, and the environment in one feedback loop. Still, even supporters recognized the fragile boundary between correlation and causation. After nearly half a century of experiments, the proof of consciousness directly shaping physical systems remained elusive. The numbers refused to decide the argument. Yet something deeper had shifted, the willingness to question the assumed separation between observer and observed. Each laboratory, in its own way, eroded the wall dividing measurement from experience. By the time Roger Nelson retired, he saw GCP, IONS, and HeartMath less as rival efforts and more as facets of a single ongoing experiment, the human attempt to catch itself in the act of existing. "We were never proving psychic influence," he said in an interview. "We were documenting curiosity, how reality responds when people look at it together." Perhaps that's why, even as peer-reviewed journals grew cautious, public interest surged. These projects gave form to a hunger modern science seldom feeds, the desire to see connection quantified. Whether through random bits, magnetic fields, or synchronized heartbeats, they transformed intangible longing for unity into streams of measurable data. And though the instruments hummed quietly in labs from California to Geneva, the real network extended through every participant who stared at a screen, focused intention into silence, or simply wondered if their thoughts fluttered somewhere inside those numbers. Because despite decades of debate, one observation kept returning. Whenever humanity shared a powerful emotion, whether sorrow or collective hope, scattered technologies across the planet sometimes blinked in sympathy. No one could say why, but the repetition itself felt meaningful, as if the universe occasionally winked back. Patterns of collective emotion. Across 20 years of data, one theme kept surfacing in the Global Consciousness Project's records. Whenever large numbers of people shared the same feeling, the world's random data streams seemed to lean very slightly away from chaos. Not enough to prove anything, yet too consistent to ignore. Roger Nelson called these episodes patterns of collective emotion. They were statistical ripples that appeared when humanity's attention converged, like faint echoes overlapping across continents. To trace those ripples, analysts at Princeton cataloged each period when public emotion synchronized on a mass scale. Some examples were grim: earthquakes and tsunamis, assassinations, terrorist attacks. Others were joyful: royal weddings, global concerts, celebrations marking a new millennium. In ordinary time, the eggs produced smooth, balanced noise, half ones, half zeros. But during these shared experiences, the output gently tilted. The shift rarely exceeded fractions of a percent, yet cluster analysis revealed that alignments occurred far more often than random probability predicted. The Indian Ocean tsunami in December 2004 became a central case. In the aftermath of the waves that killed over 200,000 people, cumulative deviation graphs rose sharply, tracing a smooth arc beginning hours before the first news bulletins and tapering off days later as mourning rituals spread worldwide. Critics argued coincidence, supporters saw the signature of global grief. For Nelson's team, it didn't matter which interpretation prevailed. What mattered was that the machines had again synchronized with an emotional moment that unified billions of hearts. When analysts compared the tsunami curve with the pattern produced during Princess Diana's funeral 7 years earlier, they noticed an eerie similarity. Both graphs showed long, slow upward drifts without the random zigzags typical of baseline periods. Statistically, the probability of two independent events sharing the same shape by pure chance was minimal. The project archivists pinned those plots side by side on the lab's bulletin board, visual reminders that numbers could resemble emotions when large enough minds felt together. Yet not all intense moments produced anomalies. The GCP network remained silent through many large tragedies and even some global celebrations. That inconsistency kept debate alive. Perhaps, some theorized, the key variable was emotional coherence, how united the world's focus truly was. When attention fragmented across conflicting feelings, the field, if it existed, scattered too. Emotional unanimity might be the unknown factor driving the effect. To explore that hypothesis, researchers compared their database with independent sociological indicators: frequency of global news coverage, volume of online communication, sentiment analysis of media language. The overlap was striking. When worldwide narratives converged on a single theme, whether sorrow, awe, or hope, the GCP's entropy readings tended to drift most noticeably. When chatter dispersed, randomness returned. Even if consciousness wasn't directly influencing the machines, the data mirrored humanity's collective focus as mediated by information itself. At HeartMath Institute, scientists studying heart rate variability were observing something similar within biology. During synchronized group meditations, participants' heart rhythms often became phase-locked, beats rising and falling together despite physical separation. HeartMath's global magnetometers occasionally showed faint correlations with GCP spikes. Taken together, these findings hinted at multi-scale coherence: physiological, social, perhaps even environmental. No proof of telepathy, but evidence that shared emotion organizes systems across layers of complexity. One particularly telling episode occurred during the worldwide rescue of trapped Chilean miners in 2001. As live broadcasts displayed the first man emerging from the shaft, the GCP's network produced a gentle but sustained deviation, positive polarity, meaning increasing order. To statisticians, it could have been chance. To observers, it felt like hope made visible in data. It became the project's symbol of collective relief, balancing the darker anomalies tied to sorrow. Even joy leaves fingerprints, Nelson remarked softly during a conference that year. By comparing hundreds of events across decades, analysts began to notice that emotional tone seemed to matter less than intensity of shared attention. Tragedy or celebration, both carried weight if global minds resonated in unison. In that sense, the network behaved like a mirror to empathy itself, registering humanity's moments of greatest alignment. One graduate student described it as a pulse of participation, a metaphorical heartbeat of civilization hidden inside random digits. Skeptics countered that such interpretations substituted poetry for physics. They pointed out that media coverage creates synchronous behavioral patterns. People turning on televisions, using devices simultaneously, which could inadvertently introduce correlated noise into electronics worldwide. Perhaps routers and internet infrastructure subtly aligned data flows, producing artifactual coherence mistaken for consciousness. The GCP team ran control analyses using redundant servers disconnected from human traffic. Deviations persisted. That didn't eliminate environmental explanations, but it weakened the most obvious ones. Another criticism centered on human psychology itself: confirmation bias disguised as discovery. With thousands of potential events each year, analysts might unconsciously gravitate toward those showing interesting shapes. Nelson acknowledged that risk, but emphasized cumulative statistics over anecdote. When all formal studies were combined, more than 500 global events logged through 2015, the aggregated probability of the observed deviations arising by chance was still below 1 in a million. Not definitive, but tantalizing. Beyond statistics, the GCP's significance evolved into something more humanistic. Charts of synchronized randomness began circulating online after major news stories, offering people a way to visualize collective feeling. In moments of crisis, visitors would refresh the project's webpage, oddly comforted seeing graphs rising or falling, as though empathy itself left measurable traces. Sociologists later described this as ritualized data empathy, using quantitative patterns to process shared emotion. Even if the spikes meant nothing physically, they symbolized togetherness in numerical form. As the digital age accelerated, global attention became more immediate, more simultaneous. Social media turned every event into a real-time synchronization experiment. Nelson's successors noticed subtle increases in baseline correlation within the network, tiny hints that humanity's interconnected communication might amplify whatever phenomenon they had been tracking. Whether that indicated strengthening collective coherence or simply more similar technological noise, no one could be sure. What was clear was that human emotion and information systems were intertwining like never before. Philosophically, the pattern forced an uncomfortable question. Maybe the GCP wasn't revealing communication between minds and matter at all, but between minds through matter. The machines, impartial and cold, might simply serve as conduits through which human stories reorganize randomness into meaning. In that view, consciousness doesn't bend physics, it organizes attention, and attention shapes interpretation, which then feeds back into reality's narrative fabric. The field, if real, might be not electromagnetic but informational, a web of shared perception constantly rewriting probability within itself. Late-night conversations at Princeton often turned to metaphors. One researcher compared the network to wind chimes scattered around the world. When the air is still, each chime rings alone, she said. When the storm passes, they all tremble together. Whether that wind belonged to emotion, data traffic, or something deeper didn't matter. The synchronization remained measurable, beautiful, and hard to explain. When Roger Nelson retired, he summarized 2 decades of study with measured humility. The data show that when people care about something at the same time, our instruments sometimes notice. Maybe that's enough. Maybe that is global consciousness, our shared capacity to notice together. As he said it, you can almost feel that pause. The moment when a scientist stops being just a scientist and becomes part of the mystery they once measured. Supporters took that line as validation, skeptics heard metaphor. Either way, the GCP had mapped a strange cartography of feeling. An atlas drawn not with boundaries of land, but with moments when humanity forgot separation. In cold statistical graphs, people glimpsed something warm and familiar. Grief, joy, awe, compassion, all rendered as faint deviations in binary code. In the end, the numbers offered no definitive physics, only the recurring whisper that emotion leaves footprints soft enough for probability to feel. The machines never spoke in sentences, but their collective murmur seemed to echo a single idea, that meaning itself might possess gravity, capable of bending the random just slightly toward the shared. And if that's true, maybe you've already felt the pull. Consciousness, intention, and physics. For as long as humans have wondered what thought truly is, the same question echoes beneath every experiment in the Global Consciousness Project. Can consciousness itself influence the physical world, or does it merely observe? To most physicists, the answer is obvious. Mind is biology, and randomness belongs to mathematics. Yet the GCP's stubborn irregularities force a deeper curiosity. If meaning correlates with measurable variance, might consciousness and matter be part of the same conversation, conducted in the language of probability? The idea isn't new. In the early 20th century, quantum physicists discovered that observation changes outcomes in unpredictable ways. When a photon passes through a double slit unmeasured, it behaves like a wave. When it's observed, that wave collapses into a definite path. The act of measurement, somehow, alters reality's behavior. For generations, scientists have debated whether consciousness participates in that collapse, or whether detectors merely interact physically with what they record. The GCP's findings revive the old argument with real-world data. Maybe observation scaled up, in collective form, can ripple through systems far beyond the microscopic. Roger Nelson avoided direct references to quantum mechanics in his reports. We measure correlation, not cause, he would insist. Still, when journalists asked how the effect could exist, the analogy was irresistible. Quantum uncertainty, human attention, collapsing waves. It sounded like theoretical permission for impossible things. But careful physics draws distinctions. In laboratories, quantum effects vanish at macroscopic scales. Environmental decoherence ensures that particles' delicate superpositions dissolve long before they reach our sensors. For consciousness to influence random number generators directly, some missing bridge between awareness and quantum mechanics would need to exist. A few theoretical mavericks tried to build that bridge. The British physicist Brian Josephson, a Nobel laureate, suggested that consciousness might operate as a form of information field capable of subtle coupling with physical systems. Others, inspired by information theory, proposed that randomness itself could be a conduit. If the universe is fundamentally informational, then fluctuations in entropy, the raw unpredictability of data, might be susceptible to organized intent, however faint. The GCP's anomalies, viewed through that lens, become not miracles of telekinesis, but whispers of informational resonance. Still, the mainstream position stayed grounded. Without replicable, controllable effects, physics could not accept new forces. Bayesian analyses consistently favored the null hypothesis. Yet even among skeptics, a philosophical unease lingered. Quantum theory already implies that the observer cannot be removed from observation. Experiments at microlevels demonstrate non-local correlations, particles influencing each other instantaneously across space. If entanglement violates distance, could collective awareness, in principle, behave similarly within complex systems? The idea remained speculative, but it kept returning in conferences, quietly threaded between equations and curiosity. Another lens came from psychology rather than physics. Instead of asking how minds might change matter, some researchers asked why randomness responds when meaning intensifies. Human attention is a limited resource. When billions focus simultaneously, the informational landscape of Earth transforms. Media signals, electromagnetic broadcasts, synchronized physiological rhythms. Perhaps random number generators, nestled within that flood of correlated human activity, register macroscale order created not by telepathy, but by behavioral synchronization. This explanation required no new physics, only an acknowledgement that technology forms part of our collective nervous system. Consciousness, then, influences hardware indirectly by shaping the environment around it. Nevertheless, a residue of genuine mystery persisted even after environmental models were considered. The strength of certain deviations, like the pre-event drifts before disasters, could not be fully explained by simple network alignment. How could machines begin to cohere 15 minutes before an event unannounced to humans? That temporal inversion haunted analysts. To believers, it hinted that consciousness wasn't bound by linear time. To scientists, it pointed again to coincidence or hidden biases in timestamp alignment. Both camps faced the discomfort of uncertainty, where neither randomness nor intuition offered closure. Some proposed that the intersection between physics and awareness might lie in complexity theory rather than quantum mechanics. In complex systems, small perturbations can cascade through networks to produce emerging order. The butterfly effect rendered mathematical. Conscious attention, if modeled as an enormous pattern of global behavior, could act as such a perturbation. Slight synchrony in decision-making, timing, or emotional rhythm might be enough to tip statistical aggregates away from pure noise. In this view, consciousness doesn't create new forces. It magnifies subtle correlations already latent in collective behavior. Random number generators, designed to measure exact unpredictability, would simply make these ripples visible. During lecture tours, Nelson would describe the data's behavior using gentle analogies drawn from everyday physics. Think of randomness as water in a calm pond, he told one audience. Every person is a raindrop. When billions fall at once, the surface trembles in patterns that appear organized. We're not moving the water directly, we are the water. The metaphor replaced metaphysics with interconnected identity, offering meaning without defying science. Whatever the mechanism, collective states seem to correspond to measurable coherence, bridging subjective experience and objective data through shared timing. Meanwhile, parapsychologists experimented with tighter laboratory controls. Using isolated quantum random sources, they instructed participants to try influencing outcomes while EEG and heart rate monitors recorded physiological coherence. Results often showed that small statistical anomalies coincided with heightened emotional alignment rather than with focused mental effort. It wasn't willpower that mattered, it was state of resonance. Emotional synchrony produced slight order from chaos, suggesting that the conduit wasn't thought as intention but feeling as coherence. Physics might one day model that through coupled oscillations, the same principle behind metronomes that fall into rhythm when placed on the same platform. Other theorists stretched further, invoking the zero-point field, the quantum vacuum bubbling with spontaneous particles. If consciousness existed as a non-local field modulating that background, they argued, minute statistical nudges could arise naturally when collective attention resonated with physical vacuum fluctuations. These hypotheses often attracted criticism for lack of testable predictions. Yet even critics admitted their symbolic power. They kept conversations open between what physics knows and what human experience intuits. That observation and reality are entangled in ways our equations only begin to describe. As the 21st century progressed, computational physicists re-examined the GCP dataset using simulations. When they modeled a network of random sources interacting through a shared informational environment, not energy or magnetism, but synchronized data streams, the observed anomalies could indeed emerge spontaneously. The simulation suggested that coherence doesn't require mysterious forces. It can arise statistically when separate systems inadvertently share timing. But that still echoed the philosophical heartbeat of Nelson's project. Meaning manifests through synchronization. Whether mechanical or mental, the result is the same pattern, order born from collective alignment. By late interviews, Nelson's tone softened from certainty to wonder. Maybe physics won't find a new particle for consciousness, he said. Maybe it already includes it, hidden in the relationships we haven't recognized yet. He often compared human awareness to gravity. Invisible, universal, shaping trajectories without direct contact. Gravity doesn't choose objects, it simply acts as curvature in space-time. Consciousness, he suggested, might be curvature in possibility space, bending probability ever so slightly when minds align. For mainstream science, those metaphors remained poetic speculation, yet they pointed toward a broader question of ontology. Is consciousness a product of matter, or the stage upon which matter performs? If the universe arises from information, and information requires awareness to exist, perhaps physics and consciousness define each other reciprocally. In that context, the Global Consciousness Project becomes less an anomaly study and more an exploration of cosmology disguised as statistics. At scientific symposia on quantum foundations, some researchers began using the GCP as pedagogical speculation. They presented it not as proof of psychic phenomena, but as a thought experiment reminding physicists that their discipline's core equations already encode unpredictability. The network's faint order in randomness mirrored the deep paradox of physics itself, that certainty emerges from uncertainty, structure from chaos. Maybe the universe is a probability field learning about itself, one commentator remarked. Our experiments are simply how it pays attention. In recent years, neuroscientists exploring integrated information theory have been flirting with similar notions, framing consciousness as a fundamental property associated with complex systems' informational integration. According to that model, awareness doesn't require mystical explanation. It's an intrinsic aspect of any system capable of unified experience. Extrapolated globally, the Earth's collective informational networks, humans, machines, data, could embody a rudimentary planetary consciousness. GCP's data, then, might represent statistical footprints of that integration, the world noticing itself for brief, intense moments. Whether these frameworks will converge into formal physics remains unknown. Empirical replication still reigns as the gatekeeper of scientific truth. But even among methodical skeptics, the experiment's allure endures because it captures something both ancient and technological, a reminder that consciousness remains the one phenomenon science continuously measures from within. We study it using tools that it itself invented. Every random number generator, every server, every calculation used to test the mind's reach is ultimately the mind studying its own reflection in data. In that recursive loop lies the heart of the debate. Perhaps consciousness doesn't change physical reality. Perhaps it is the process by which reality defines itself. Probability may only appear random until attention binds certain possibilities into story. The Global Consciousness Project didn't prove physics wrong. It revealed that meaning and measurement are inseparable, twin lenses through which the universe peers at its own uncertainty and briefly, collectively, becomes coherent. The people who experience the field. Long before the numbers reached spreadsheets or statistical charts, they were lived experiences, felt as a subtle hum, an invisible tug between people who swore they'd sensed something in the air. The Global Consciousness Project studied bits, but behind those bits were hearts and stories. Researchers began collecting testimonies from those who participated in mass meditations, from laboratory volunteers, even from ordinary people who said they felt strangely synchronized during world events. Their words turned the cold graphs into something quietly human. One meditation facilitator in California recalled leading a group session on the day of the 2004 tsunami. Halfway through, everyone opened their eyes at once, she said. No alarm, no signal, just this flood of grief that we couldn't place until the news came. When researchers later compared timestamps, her account aligned eerily with the first reports of the waves. To skeptics, coincidence. To participants, evidence that emotion can travel faster than information. At Princeton, Roger Nelson encouraged those who experienced uncanny synchronicities to write directly to the project. Letters poured in, handwritten notes, emails, recorded messages, from people describing moments when they felt connected to strangers across continents. A nurse in London wrote about holding a patient's hand during the 9/11 broadcast and sensing, as she put it, a world-sized heartbeat. Nelson archived every message, not as proof but as context, a human parallel to the data's cold lines. Numbers tell one story, he said, but sensations tell another. Among GCP's volunteers, shared intuition became almost routine. Host operators of the random number generators reported spontaneous correlations. LEDs flickering slightly brighter during major events. Computers freezing at the exact instant global coverage intensified. None of it was scientifically unusual. Every explanation had a technical possibility, but the pattern repeated. The machines seemed to echo human collective tension, a mirroring that blurred boundary between observer and observed. Inside meditation circles linked to HeartMath's Global Coherence initiative, similar stories unfolded. Participants described entering deep calm, only to feel waves of elation or sadness unconnected to their personal lives. Heart rate sensors captured synchronous oscillations between distant groups. In some sessions, thousands logged coherence in near-identical rhythms. Researchers compared those physiological curves to GCP's data archives, finding minor overlaps during massive synchronized events like World Peace Day meditations. The alignment was faint yet reassuring, a bodily confirmation that collective emotion might reverberate through both flesh and circuitry. Psychologists studying these experiences noticed an interesting outcome. People who engaged in group coherence exercises often reported increased empathy long after the sessions ended. The practice of focusing on global well-being appeared to recalibrate perception, lowering stress while heightening sensitivity to subtler emotional cues. Even if no magnetic or quantum field linked them, shared intentions seemed to carve invisible channels of compassion. Maybe coherence doesn't travel through space, one participant joked. Maybe it expands it. Researchers themselves weren't immune to the effect. After 2 decades inside those laboratories, many admitted that the work transformed their own understanding of connection. Brenda Dunn, who had once co-led the pair lab, described walking through Princeton's quiet hallways at night, hearing the faint rhythmic clicking of RNG machines. Every click felt like a pulse, she said, as if the lab itself was breathing with us. These weren't confessions of belief in telepathy. They were acknowledgments of awe, the sense that objective study had crossed paths with subjective mystery. During the first global meditation synchronized by IONS in the 201s, thousands tuned into a live webcast led by astronauts and scientists. The collective focus lasted just 15 minutes. Later analysis found a modest correlation in the GCP's network during the same window, again tiny, yet distinct. When participants were asked what they felt, responses converged: stillness, clarity, warmth spreading through the chest. Statistically irrelevant perhaps, but emotionally undeniable. Those experiences created community far stronger than p-values. In later years, Nelson spent less time defending methodology and more time listening. He attended conferences where attendees stood in circles, eyes closed, palms open, visualizing connection across the planet. When they finished, he'd quietly bring out his laptop, pull up real-time RNG readouts, and watch the fluctuating lines stabilize. Sometimes they drifted upward toward coherence, sometimes not. He never claimed cause, only smiled at the symbolism. These moments remind us that measurement isn't separate from participation, he said. That line resonated with new generations of consciousness researchers who viewed science as an evolving dialogue rather than a fortress of control. They argued that subjective accounts weren't noise, they were data of another kind. Qualitative reports revealed patterns in human narrative, matching the quantitative anomalies in sensors. Both described oscillations of unity and disconnection repeating across cultures. When tragedies struck, heart coherence logs and RNG graphs alike bent in tandem, but so did prose and personal journals collected afterward, vocabulary densifying around shared emotion. Meaning, statistically or linguistically, behaved as a field. Critics dismissed this approach as anthropological mysticism. Yet even among skeptics, something in those stories compelled attention. A statistician known for debunking parapsychology admitted after meeting GCP participants, "I still think the numbers prove nothing, but I can't ignore the sincerity of their experience. Maybe their belief is the phenomenon." That comment captured an unmeasurable truth. Belief itself can reorganize perception, altering how individuals relate to randomness and perhaps to each other. The field might not reside outside at all, but emerge in collective imagination. an effect powerful enough to model itself in data through cascading behaviors. At HeartMath, long-term volunteers monitored environmental magnetometers in real time. When global events broke, a royal wedding, a natural disaster, they'd text each other screenshots of concurrent spikes. The messages often included hearts or short reflections. We felt that one. Over time, the data streams became emotional diaries as much as scientific records. Each fluctuation told a story of attention, compassion, or curiosity, focusing momentarily on the same coordinate in shared time. One evening near the project's 20th anniversary, Nelson hosted a small gathering of former colleagues and volunteers. They projected 2 decades of cumulative deviation graphs across a darkened room, thousands of tiny red dots forming a faint upward curve toward order. For newcomers, it looked like statistics. For those who'd lived it, the chart resembled memory itself. As silence filled the room, one participant whispered, "It looks like a heartbeat." No one corrected her. The scientists in attendance could parse every contingency, hardware drift, environmental correlation, random clustering, but none of that erased what they'd felt working side by side on an experiment that blurred the border between machine and meaning. They had become witnesses not only to data, but to a human yearning measured one bit at a time. When interviewed later, Nelson reflected on how the project had shifted his sense of purpose. "We began by asking if consciousness could influence machines," he said. "We ended up realizing the machines only showed us how deeply we influence each other." That realization, he believed, was the project's true legacy. Not numbers proving telepathy, but experiences proving empathy. The recognition that global emotion isn't metaphorical. It's measurable in physiology, in behavior, sometimes even faintly in silicon. For many participants, that idea changed lived reality. Meditation facilitators reported communities becoming more compassionate. Volunteers said they felt less isolated knowing instruments somewhere were listening to human feeling. The Global Consciousness Project might never persuade physics, yet it gave countless people permission to sense belonging on a planetary scale. And perhaps that's the quiet answer the data refused to articulate. Consciousness doesn't act upon the world like force. It participates in it like resonance. The people who experienced the field weren't witnessing miracles. They were discovering what collective awareness feels like when rendered visible, however faintly, through numbers. In the end, the field's proof wasn't in statistical significance or sigma values. It was in those shared human moments when randomness aligned with empathy and everyone, for an instant, felt the same unseen pulse running through the world and through themselves. What the data really shows. After 2 decades of recording, cross-checking, and arguing, the Global Consciousness Project had accumulated more than 6 billion data points. What did it all amount to? The simplest answer depended on who you asked. To believers, it was evidence that minds create measurable ripples in matter. To skeptics, it was proof only of humanity's endless pattern-seeking reflex. But when the project's final audits concluded in the late 200s, the database itself told a quieter, more complicated story, one that didn't need mysticism or debunking, only honesty. Across hundreds of registered world events, the overall deviation from pure randomness remained tiny, a fraction of a percent. If you averaged the entire archive, most days looked perfectly normal. A handful, though, displayed smooth curves of improbability that refused to vanish under reanalysis. Each spike coincided with collective focus, terror attacks, natural disasters, mass celebrations, global meditations. None provided proof of a causal link, yet cumulatively the odds of so many coinciding curves hovered well below standard chance. The pattern wasn't strong enough to change physics, but it persisted through statistical firestorms, surviving every attempt at erasure. To Roger Nelson, that persistence meant something profound, but not supernatural. "Maybe consciousness doesn't push bits around," he said. "Maybe it just organizes the way we look at them." In that phrasing lay the project's quiet evolution, from experiment about psychic force to reflection on perception itself. The GCP had become a mirror suspended between humanity and data, measuring less the world's hidden field than our desire to find connection within it. Independent reviews reinforced both halves of that paradox. On one side, Bayesian tests favored the null hypothesis, no reproducible mind-matter effect. On the other, cumulative deviations across the database defied total dismissal. Statistician Dean Radin summarized it best. "The effect is small, but it's there, as persistent as background music you can't turn off." Many interpreted that soundtrack as evidence of subtle coherence woven through collective emotion. Others called it artifact stacked upon artifact. The disagreement itself became data, an ongoing oscillation between faith in meaning and faith in math. Re-examined from a sociological view, the numbers trace something different altogether, a chronicle of shared attention in the digital age. Each anomaly marked moments when billions synchronized, not mystically, but informationally. As New Year's fireworks ignited across time zones or breaking news froze conversations worldwide, the same data streams that powered human communication also delivered microfluctuations in electronic systems. In that sense, GCP's graphs documented the rise of global connectivity itself, the birth of a planetary nervous system humming through bandwidth and emotion. Critics pointed out that correlation with attention doesn't equal consciousness affecting machines. It simply reveals that humans and technology breathe the same statistical air. Yet even through that pragmatic lens, the GCP achieved something extraordinary. It captured the texture of collective experience as numerical weather. Like atmospheric sensors measuring pressure, its eggs recorded the climatology of emotion. Storms of fear, calms of celebration, waves of empathy sweeping through circuits and society at once. Inside the GCP team, divisions softened over years of shared work. Some remained cautious empiricists, others leaned toward metaphysics. What united them was curiosity about why slight order kept appearing amid randomness. Software audits found no consistent mechanical cause. Environmental monitors ruled out geomagnetic interference. The remaining possibility, however defined, was that human meaning itself behaved as an organizing principle, not as external force but as shared interpretation turning noise into pattern. Awareness wasn't acting on machines, it was emerging through them. When universities reviewed the project for closure, Nelson argued that its value wasn't in proving psychic phenomena, but in chronicling an era's collective psyche. Distilled to essence, the data revealed our fascination with the boundary between mind and matter, our hope that connection could be quantified. Each entry in the database was a time-stamped heartbeat of civilization asking, "Are we moving together?" The answer, written in near imperceptible deviations, was both yes and no. Statistical ambiguity mirroring human ambiguity itself. Philosophers later compared the GCP archive to medieval star charts, imperfect maps drawn by those who believed meaning shimmered within the cosmos. They were wrong in details yet right in spirit, documenting humanity's instinct to read itself into the universe. The Global Consciousness Project continued that lineage using silicon instead of parchment. Its tiny fluctuations became modern. Constellations, random dots traced into stories of empathy and fear. Whether the lines we draw between them reveal reality or imagination remains the enduring mystery. By 2019, Nelson retired, leaving the servers running under volunteer supervision. The website still updates, quietly appending fresh rows of zeros and ones. Visitors stop by after every worldwide shock, a pandemic announcement, a global protest, a viral act of kindness, checking whether the red line bends again. Sometimes it does, sometimes not. Either way, the act of looking transforms data into ritual. People no longer seek scientific proof. They seek confirmation that collective feeling is real. And in that sense, the GCP fulfills its name. It generates consciousness globally, not through measurement, but through participation. When modern analysts revisit the numbers, most conclude that the anomalies fall within the boundaries of complex but explainable statistics. Yet even they admit an intangible residue. The timing of certain curves aligns with humanity's most charged hours too perfectly to dismiss without a trace of wonder. The project sits forever on that thin line between coincidence and connection, between cold probability and warm meaning. Philosophically, the findings suggest a different kind of evidence, one pointing inward. The patterns demonstrate that humans respond to shared emotion by searching for reflection, turning chaos into coherence through perception. Whether or not collective thought bends physical randomness doesn't matter. The experiment proved that collective thought bends us. It organizes communities, shapes empathy, and reminds us that knowledge and belief intertwine more tightly than science likes to admit. In classrooms now, instructors sometimes display a GCP plot alongside the phrase correlation is not causation. Students debate, laugh, speculate. Then someone notices how the curve climbing through global turmoil looks uncannily like a human pulse. That moment of recognition, half joke, half revelation, is exactly what Nelson foresaw. Data evokes emotion Emotion demands meaning. Meaning reshapes data. The loop closes back on itself, an elegant feedback between observation and observer. So what does the data really show? Statistically speaking, nothing supernatural. Psychologically, everything human. It reveals how desperately we want randomness to care, how instinctively we search for signs that the universe feels with us. In an age of algorithms predicting desire, the GCP stands as both experiment and metaphor, a reminder that even in electric noise, we project the pattern of our hopes. If the project proved anything final, it's this: consciousness measures itself endlessly. Whether through machines, stories, or shared silence, the act of looking together generates the very coherence we seek. The illusion may not be shared reality. It may be the notion that reality stands apart from the sharing at all. And as each egg continues to hum in distant corners of the world, flipping its quantum coins into digital night, perhaps that's the truest outcome of all. Not evidence of minds moving matter, but of matter quietly mirroring the mind that wonders. Resolution and reflection. After everything measured, debated, and doubted, the numbers still whisper the same quiet truth. They can't prove that minds shape matter, but they do prove that meaning shapes minds. The Global Consciousness Project began as an attempt to record the impossible and ended as a mirror showing how deeply we want to belong to something greater than chance. In those faint deviations and fragile correlations, humanity saw its reflection, a pattern forming only when attention converged, fading when focus scattered. The machines never confirmed a cosmic field. They revealed that awareness itself behaves like one, connecting observers through shared story. Science demanded replication, and replication never came. But connection came anyway. Labs collaborating across continents, people meditating together, strangers refreshing data graphs just to feel less alone. Every glance at those rising curves became a small act of communion. Maybe that's the experiment's real success, proving not paranormal influence, but the persistence of wonder even when results stay undecided. The data never lied. We simply kept asking it to say more than numbers can. So what remains is perspective. Consciousness didn't rewrite physics. It reminded physics that observers are part of every equation. And every time billions feel together, randomness bends beneath collective interpretation, turning noise into narrative, probability into pulse. Maybe the illusion isn't that we're connected. Maybe it's that we ever thought we weren't. Because the truth hiding in all those numbers isn't just about data, it's about us. Every time billions of minds align in fear, hope, or awe, something invisible hums beneath it all. And somehow the math remembers. If you're still curious about how these invisible synchronies echo in today's quantum and consciousness research, check out the next film. It follows scientists mapping real-world coherence across minds, machines, and planetary fields. Subscribe so you don't miss what they've discovered, because the story of awareness isn't over. It's just beginning to notice itself. And now, you're part of it.